So in this example, we're going to solve the differential equation y squared e to the xy squared plus 4x cubed dx plus 2xy e to the xy squared minus 3y squared dy equal to 0. First order, first degree differential equation. So this equation is in the general form of some function of x and y dx, some function of x and y dy equal to 0. So in this case, we can define this m and n function here as m of x and y is just the argument of this first term dx. So we define that as that argument. And then our n of x and y is the argument of the second term dy. So here we just put that here. And so as we do with exact equations, to check for exactness, we'll take the partial derivative of m with respect to y. And so the only term that has any dependence on y is this first term. And so when we take that, we have to do the chain rule for the two different terms. So 2y e to the exy squared plus 2xy cubed e to the xy squared. Likewise, we want to take the partial of our n function with respect to x. And so again, same thing, chain rule. And so when we do that, the first term, we get this 2y e to the xy squared. And then we do the chain rule application of that, and we get the second term. And we see that our partial of m with respect to y is in fact equal to the partial of n with respect to x. We get the same answer for both of those. This, by definition, is an exact equation. So we have confirmed our equation is exact. So this being the case, there's two different ways to solve an exact differential equation. The first approach is a little more direct. So in that approach, we define this new function, mu of x and y, and it's defined as the integral or the antiderivative of the m function of x and y just with respect to x. So here we take our m function that we defined in the previous slide, we integrate it with respect to x, and when we do, this is basically u e to the u, so we'll get e to the xy squared, the 4x cubed become x to the fourth, and then we're going to stick some arbitrary define some arbitrary term just in y, phi to the y. So that's perfectly valid, because if we were to take the derivative to go backwards in this equation, if this function is only in y, it would be 0. So you would have no hint of it here. And this is to be expected though with an exact equation, because we know there is some y term there, and that's what we're solving for. So that being the case, now that we have mu of x and y defined, we now want to take the partial derivative of mu now with respect to y. And so when we do, we get this first term, because this is the only term here that has any dependence on y, so we get this 2xy e to the xy squared. The x to the 4 has no dependence on y, so it'll just be 0. And then we'll just take our phi function of y and just say the first derivative of that function. So now we can take this and set this equal to our n function. Remember that we defined it from the second term here. And so when we do, we set that equal to that argument there. So now when we do that, we should see or notice right off that we have two common terms on each side here, so those could cancel out. And so when we do, that tells us then that our first derivative of our phi function of y then is minus 3y squared. So we can just take the integral of that in terms of y. And when we do, we find out that phi of y is equal to minus y cubed. So now we can substitute this back into our equation we had on the last page for mu. And when we do, we see that we have e to the xy squared plus x to the fourth minus y cubed is equal to c. And so this is the general solution for the equation above. Again, we could solve for the c if we had some boundary conditions, but we don't. So we just leave that as an arbitrary constant. So now we remember that there is a second method, which is more by inspection. And here we recall that we're looking for something in the general form of y dx plus x dy, remembering that that is the basic definition for the chain rule. So that would define some derivative of xy that we could work backwards when we're integrating. So to do this, we're going to regroup our original equation. So we have our 4x cubed dx, which comes from here. We have our minus 3x squared dy, which comes from here. We have our y squared e to the xy squared here, and then our 2xy e to the xy dy here. And here's where we are observing we have some chain rule format for this function. So now we can just directly integrate this, and when we do, the 4x cubed term here, the 3y squared term here, and then this is going to be just e to the xy squared is what this chain rule works out backwards. And again, we get back to our original solution that we got using the first method. So using either method, we should get the same result.